Hi guys, again, I'm sorry about that. I don't know what happened. We got disconnected. That's not good. Anyway, we didn't do anything. So for those who are probably watching the recording, nothing happened, okay? Just when I started and I just clicked on record when the thing froze and then restarted. Anyway, and apparently the entire site went down for some reason. Anyway, so today, actually, we're going to be doing some problems from chapter 29. I know the problem that we did was kind of a doozy problem, basically. It was a loaded problem. And so we're going to build on that, actually. And we did that last time. So we're going to build on that problem. And then we're going to do a similar problem actually to it. It's problem 54. I believe problem 54 I gave as an exam, or at least something similar to it, as an exam in the past in another college, actually not in here. So that was kind of a nice problem. And problem 54 is similar to problem 59, with the exception that in problem 54, you really don't kickstart the rod. It starts on its own, okay? And then we're going to do a couple of more problems, and then we're going to start chapter 30. So let me get into chapter 29 problems first, and then share with you the screen so that we will talk about these problems. So is this chapter 29? Yes, it is. There was something from chapter 28 that I didn't really do in purpose because I thought we can defer it to chapter to chapter 30, because what happened is when I do it in chapter 28 it will be forgotten. So and that is to calculate basically the magnetic field created inside the solenoid. There are two types of solenoid. There is the straight out solenoid, and there is the so-called, basically it's like a donut shape, and then you wrap the wire around it, and that gives you also another type of solenoid, and it's used extensively in electronics. This is not a donut shape. This is a regular solenoid, the one that you see in here and in here too, actually. No, actually not this one, this one. Okay, so those are some types that you find in electronics. Actually, there is one in here, right there. Two of them, actually. Okay. So we're going to get into those shapes, okay, and back where it was, and then we do chapter 30. So we'll need the calculation about the solenoid and how to find the magnetic field created inside the solenoid, because you will see the whole point of it will rely on that idea. So let's get started with this chapter. So let me share with you a screen. First of all, before I start the chapter, let's do some problems from chapter 29, because we only did one problem. Are you guys looking at my notes in here for CH29? It says problems. You guys hear me?
Yeah, we see it.
Okay, very good. Thank you. So the next problem I thought we could do is problem 54, because it's immediately related to this problem also from chapter 29. And problem 54, if you look at it, by the way, problem 31 is not too different from the other two problems, from these two problems too. Okay. And so is problem, so many problems are similar to this one. Problem 65 also is not different. Okay. So problem 54. Problem 54, it says a bar of length L equals 36 centimeters, or 0.36 meters, okay, is free to slide without friction on a horizontal rails as shown in the figure. So what the figure shows in here is that there are horizontal rails. Here they are. And there is a bar in here. So let me draw it with a thicker line. Let me go back into my regular. But then you have a battery in here, in this direction. And usually you have a switch somewhere. Okay, and the EMF of the battery is given. So the battery is pointing in this direction. You have to remember that. It's very critical that you have to get the sign correctly in here. And so the current that the battery is trying to drive is in this direction. Okay. As a matter of fact, the rays, they have a thicker shape, but that's fine. So it's free to slide without friction on the horizontal rails. A uniform magnetic field of 2.4 Tesla. That's a very strong magnetic field, by the way, 2.4 Tesla. So let's draw the magnetic field. It's in the entire space in here. And it's, according to the picture, is pointing into the screen. We want it to be uniform, that's why. So this is B pointing into the screen. And B in magnitude, so let's write what we're given in here. So we have L, we are given also B to be 2.4 Teslas. So B is 2.4 Tesla. That's the strength of the magnetic field. And also is directed into the screen as of the plane, into the plane as shown. So they give you the direction. At what end of the rails there is a battery EMF 12 volt. So the EMF of the battery is 12 volt. Okay. And a switch S. So we have a switch in here to close it at some point. Okay. The bar has a mass M of 90.9 basically, or 900 grams, so 0.9 kilograms. Okay, we have two sig figs, by the way, this entire problem. And the resistance R, so the resistance R of this is given to be equal to 5 ohms. So unlike the previous problem, this has numbers. So you really have to pay attention to these numbers and make sure that you do all of the math. Okay, again, just disclaimer, not disclaimer, actually requirement. Every one of you is supposed to have a piece of paper and a pen or a pencil and doing exactly what I'm doing, not relying on just watching it. This is not a movie that you're supposed to be watching. You're supposed to do these things, okay? If you're not doing it right now, you are not doing the class. If you're not actually writing what I'm writing, drawing what I'm drawing, and doing the things, yes, it's drawn before you on the computer, on the book. But I want you to really also get the hang of doing that on your own, okay? So I'm assuming that all of you are at this point where I am at right now, writing everything. Okay, and taking notes as duly noted, because they say, for example, the resistance is negligible everywhere else except in there. They say, and I didn't write that one, that there is no friction. Otherwise, if there is a coefficient of friction, kinetic friction or something, then we have to take that into account, okay? And that is physics 4A. So it's not there. So at this point, ignore all other resistance in the circuit. So the only resistance in the circuit that matter is this one, okay? The switch is closed at time t equal to 0. So at t equal to 0, this switch is closed. So that is when we start basically calculating the step. Okay, S is closed. Now, sketch the bar speed as a function of time. Obviously, here is what's going on. We're probably going to draw it more carefully if we, at the end, we're going to do that. So this is what's going on. Initially, when the switch was open, before t equal to 0, there was no current in the circuit. So there is no reason for this one to move, because if there was a current in the circuit, this bar starts to move one way or the other, depending on which way the current is moving. If the current is moving downward as the battery is going to push it, the current is going downward, the magnetic field is into the picture. So in this case, the force that is going to result from it, the force that is going to cause this thing to move. So what you have in this case, you have this picture. You have the current pointing inward, and you have the magnetic field pointing into the screen. So the force is going to be this way. So it's going to start to move. So this is the force that is basically due to this current initially, immediately when you close it, okay? Immediately when you close it, there will be a current, which is given by Ohm's law. Ohm's law in this case basically says that the EMF is equal to Ri. So from here, this is at t equal to 0, immediately after t equal to 0. So this is not any time in the future. This is just immediately. So from here, I can find the current to be just epsilon over R, and then apply then the basically stuff from chapter 27 to find the force, and the force is going to be ILB, where L is at length, times I times B. Okay, everything is perpendicular and everything, because what is that, plus or minus? It's plus. I don't know what this. Oh, I, that was I. I'm sorry. I probably. So that's supposed to be the I that I somehow deleted and rewrote it somewhere. I mean, I rewrote it somewhere else. Anyway, so basically what we have, this is the force that is going to cause it. And again, if you are careful enough with the signs, the current will be raining down. The magnetic field is into the picture. So if you use a right-hand rule, then in this case, the force will be in this way. But then, hey, there is a problem now. If this starts to move, the flux of the magnetic field will change, because the flux of the magnetic field right now, just before everything else is happening, is this area times the magnetic field B. But because this area now is increasing as this starts to move, the flux will increase. As the flux increases, by virtue of Faraday's law, another EMF will be established, and that EMF will be given by minus the rate at which the flux is changing with respect to time. And the flux will change with respect to time by B times L times the velocity with which it's moving, because now it's going to move because of this force. So it's going to change at this rate. And it's going to be pointing in such a way to compensate, because there will be more and more field lines going to the screen. So it's going to make up field lines coming out of the screen. So it's, when it moves, it's going to compensate for this field lines that's going to encounter as they're going into the screen by making up its own ones that are coming out of the screen. Okay, and those, they need to be exactly the same number of field lines that are going in. So for it to create a magnetic field coming out of the screen, the current that is induced must be, because of this EMF now, must be going counterclockwise. So this is the current that is going to be generated now. This is induced because of this change. So there is a current being pushed by the battery in one way, and there is a current that is going to be generated now because of this induction, and the two starts to compete. Now this velocity starts to change. It's not going to stay the same, because the force now, because this current is moving in the opposite direction. So now the second law that I'm going to apply, I is pointing upward. The magnetic field is still going into the screen. So the second force that is going to come in here because of this is going to be resisting this change. And that force will be this I times L times B. And these two currents start to compete with one another. Obviously, the faster this thing is going to go, the stronger the current. And these two currents start to cancel one another until these two forces basically balance each other. Once these two forces balance each other, we would have reached terminal velocity. This is similar to a problem you guys did in physics 4A, where a person jumps from a plane with a parachute. As the area of the parachute as the person is falling down. Initially, that person, even with the parachute, they will fall down with the acceleration g. But as he gains speed, there is now a drag force that is proportional to the velocity, basically squared in that case. But it's also depending on the shape of the parachute, proportional to the area of the parachute, proportional also to the drag factor, and proportional to the density of the air times 1/2 that you guys remember from the physics 4A. As he moves faster and faster, this force now of the drag force that is pushing him upward will cancel his own weight, and at some point the two forces will cancel, and you would have reached the terminal velocity. This is similar. The acceleration starts big, and then is going to get smaller and smaller and smaller. So we're going to plot this function. We're going to plot this function, and we're going to see how v changes with time. So basically, that is what this problem is. Okay. But initially, the velocity is 0. So as the velocity increases, this value starts to increase until it cancels the other current, as this force cancels the other force. And at that point, we would have reached the terminal velocity. You would still need this current being pushed. Otherwise, it's going to come to a rest, stop, like the problem that we did last time. Okay. So part B, just after the switch is closed, what is the acceleration of the bar? So after it's closed, this is the current. So the acceleration is F equals to ma, that's all. We know F equals to ma. So the acceleration will be given by ma equals to lib. And from here, the acceleration will be just lib divided by m. And I know what I is. It's the EMF over R. So this is going to be mr. So if I'm going to plug in numbers, L is given to be 0.36 meters. So this is 0.36 meters. Times the EMF. The EMF is 12 volts. Yes, 12 volts. The magnetic field is 2.4 Tesla. The mass is 0.9 kilogram, and the resistance is 5 ohms. So if I plug in everything in here and everything is in the proper units, I should find a value. Let me see how much it is. It's going to be 0.36 times 12 times 2.4, and the whole thing is divided by open parentheses 0.9 times 5, or 4.5 that is. And the answer is 2.304. Remember, there are only two sig figs. 2.3 meter per second for every second, or meter per second squared. So that is the acceleration immediately after. So this is not the acceleration all the time. This is immediately after t equal to 0. Okay. Part C, and we're going to draw that graph, okay, so don't worry about it. Part C is what is the acceleration of the bar when its speed is 2 meters per second. We really need to find it at any time because I don't know what the current is going to be at that time. So part C, we really need to do this and check that this number holds true there. So here is what's going on. We have two EMFs now. As if I have a battery going this way, I have another battery also in the opposite direction. So this is basically what's going on. I have a 12-volt battery pushing the current this way. And effectively, I have another battery pushing the current in the opposite direction. So this is the EMF that is given, and this is due to Faraday. Okay, and I have here a resistor R. So this is how the circuit looks like. So if I take any point and draw the Ohm's law, so if the current is moving this way, for example, for my calculations in here, the drop in voltage is Ri. Okay, and in here, actually, the drop in voltage is going to be Faraday's law. And in here, actually, is going to be a rise in voltage, which is minus epsilon, is equal to 0. So in this case, I'm going to write Ri. This is the total current, actually, not just one of them, is going to be the EMF given minus Faraday's law. Now I need to write what Faraday's law in general is going to be. It's going to be just this expression. So what I have in here in actuality, Ri is equal to E, which is the EMF, which is constant, which is 12 volt, minus LB times V, okay? This is this value in here, okay? Because the flux of the magnetic field is B times the area, and the rate at which change, the width doesn't change, the magnetic field doesn't change. The only thing that is changing is this length, and it's changing at the rate of B. So if I call this one X, I take the derivative of X with respect to T, it's gonna be V. So this is the expression that I'm looking at in here. And this gives me then the current, I, to be simply equal to the EMF minus LB V over R. Now that's just a current. But I need to express now the total force, in this case, that this thing is going to be subject to as some force in here, which is this current, which I'm going to assume to be down. So I'm going to assume it's still going to be down. And so this is the current of the wire. And apply the law. So it's going to be pushing it in the opposite direction. So in this case, the force F will be going to be F is just going to be I, this current, I, times L times B, okay? Where I is just this current in here, it's equal to LB times the EMF minus LBV over R. Okay, so this is the force must be equal to MA, and MA is MdV over dt, okay? Now, I could have written this expression differently. I could have said that this force is just the sum of the two forces. The one that is pushing it this way, and that's going at constant current, and that is epsilon over R, and the other one is opposing it, and that is changing with V. So I could have argued the whole problem a little bit differently and say that this force in here, the way I drew it to begin with, and say that this is going to be subject to two forces. The first force is going to be this due to this current, which is epsilon over R times L times B, and the second one is due to this current, which is BLV times again the same thing, times LB divided by R. So there will be an L squared B squared in it. So having said that, then I'm going to write this expression now in terms of everything. So how can we tackle this expression here? Because this is actually an integral that we need to integrate from 0 to t. Because we're asked to find it at 2 seconds. So we need to integrate from 0 to 2 seconds to find the velocity at that time. So what do we do in here? So we leave dv by itself. So we're going to do like we did last time. We multiply by dt and divide by m, and divide also by this whole quantity in here. So it's going to be epsilon minus LBV. Okay, so it's going to be, everything goes away from this side. So it's going to be epsilon minus LBV. And it's going to be equal to the other side, just LB divided by R and M. So it's going to be LB over MR, and of course dt, okay? So that is the algebra that I did. All I did was basically multiply by dt and divided by m times LB minus v. Okay, we need to do a change of variable in here, and it's warranted because of the fact that I have to integrate over v, but I don't have v in the denominator. I have some complex combination of the things. So the first thing usually we do in this case is we're going to define a new variable, if you want to call it u, and u in this case is going to be epsilon minus LBV, so which means that du is equal to minus LB dV, because again, the EMF is constant. So what I have in this case is dV is simply equal to minus the new variable du divided by LB, and this is du. So what I have in here is du over u is equal to minus, because of this minus, and I have an LB in the denominator in here that I'm going to multiply by that one, so it's going to be L squared B squared over MR dt, okay? So this is the change of variable that I'm doing in here. I want to write this whole, because epsilon is constant, so I'm changing to this new variable. So I need to calculate dV, like you guys do in calculus, in terms of the new variable du, and that's how much it is. So plug in everything back, so this is the integral that I'm going to deal with. Well, if I do the integration of dx over x, we saw that yesterday or Monday. So that is actually the natural log ln of u. And u, if you guys remember, is this whole expression. So I'm going to go back, instead of dealing with the with this new variable, I'm going to go back into this expression, integrated between at t equal to 0, the object was not moving, so velocity v was equal to 0 initially. At some velocity v sub t now, so this is the boundaries of integration on one side, and the integration from the other side is simply lb squared over mr, t evaluated between 0 and t, so that is just t, okay? Again, doing the same trick like we did last time. So this is going to be ln of this number minus ln when v is equal to 0, so it's going to be ln of epsilon. And again, that is just going to be the ln of the ratio, just like last time. So if you have difficulty with this one, please let me know. So it's going to be ln of b v, and v is a function of time, by the way, now, divided by, when v is equal to 0, this expression reduces to epsilon. So I have it in the denominator because the log of a minus the log of b is just the ln of the ratio a over b. This is the properties of the natural log. So again, this is equal to minus L squared B squared over MR T. If I take the exponential of both sides, this is what we're going to have. We're going to have epsilon minus LB times B sub T is equal to, again, I multiply everything at the same time, exponential of negative L squared B squared over MR and then T. Take this to this side, take this to the other side, and now this will be a negative, so it's going to be epsilon times 1 minus exponential minus L squared B squared over MR T. And this one is equal to, on the other side, when I move it, it's going to be LB of V of T. Okay, so now we have a velocity V as a function of time. V as a function of time is the EMF divided by LB times 1 minus the exponential of minus L squared B squared over MR T. Okay. So that's basically the expression. If I'm going to plot this function, I better find what that tau is, okay? I better find what this number is. So what I'm saying in here, this looks like, first of all, like charging capacitor. Epsilon over LB should be V naught. What I thought was V naught, okay? Here is oh, wait a minute. Where is, did I miss something in here? No, that's the acceleration. We're not talking about the acceleration. If I take the acceleration now, take the derivative of everything with respect to time, that should be the acceleration. So the acceleration of this expression is going to be taking the dv over dt. Did they ask us about the initial velocity or the initial sketch the bar's velocity as a function? Just after the switch is current, what is the acceleration? What is the acceleration? So yeah, we need the acceleration, which is the derivative of the velocity. Again, the derivative of a constant is 0. The derivative of a negative, here you're going to drop the negative times the negative is going to be positive. Epsilon over LB times L squared B squared over MR. And then you don't forget that you have an exponential of L squared B squared over MR T. The L squared and the B squared cancel with the LB, and the value at t equal to 0 is exactly how we calculated it initially. So A sub t in general is going to be epsilon times L times B divided by MR times the exponential of negative L squared B squared over MR T. Now again, for t equal to 0, the exponential is just equal to 1. So we don't worry about that. It's for, and that is the value is epsilon LB, epsilon LB divided by MR, exactly how we're supposed to have found it. So it checks, okay? So A sub t, A sub 0 is exactly ELB over MR as we did calculate it to begin with, okay? So that is fine, that's good. But they didn't want us to find it at that point. They want us to find it at 2 seconds later. So it's a good idea to find what this time characteristic in here in the exponential is. Because this exponential looks like this expression for the acceleration of t in general, it looks like acceleration at t equal to 0, which we just found, by the way, times the exponential of minus t over tau, where tau is the inverse of this number. It's mr divided by L squared B squared. So I need to find tau, which is a time characteristic of the mass times the radius divided by by the resistance, L times the magnetic field. So I need to find what this tau is. Of course, the mass is 0.9. The resistance is 5 divided by L is 0.36 squared times the magnetic field, which is 2.4 squared. So tau is going to be in seconds and is going to be equal to 0.9 times 5 divided by open parentheses 0.36 squared times 4 squared 16. No, not 4 squared. 2.4 squared. 2.4 squared again. Now close the parentheses and see how much that hits. It has a tau is 6.03 seconds. I know I mentioned that the fact that this has to be 2 sig figs, but because it's not really a question that we were asked to find. So I'm going to keep the whole value in here just to make sure when I calculate a sub 2, I'm good. So a sub 2 now, after 2 seconds, is going to be a sub naught times the exponential of minus 2 divided by this tau, okay? 6. So it's going to be e to the square root of 3, basically, because 2 over 3 is 1/3 in the denominator. So let's see how much is that. So we have a naught, which is 2.3, times e to the power, open parentheses, just minus 2 over, I'm going to use the exact value, okay? I just borrowed it from the previous expression. So it gave me value of 1.65 or 1.7, actually. Let me round it up. Meter per second per second. As you can clearly see, the acceleration is going down. So it was high to begin with. Where is A naught? 2.3. What did we find it in here? Didn't I put the number in here somewhere? Yeah, 2.3 meter per second initially, but after 2 seconds, it dropped to 1.7 meter per second, okay? So it should go to 0 after a while. The acceleration should go to 0. It's going exponential, actually. Look at it. It's decaying exponentially. That is how the acceleration is. And they ask us what is the bar's terminal velocity. The bar's terminal velocity is when t goes to infinity, everything will go to, this exponential go to 0, so it will be left with 1 minus 0. So the terminal velocity will be just the EMF over LB. So Vt, so that is C, V terminal is going to be the EMF over LB times, if you like, what is the expression here? Times 1 minus exponential of t over tau when t goes to infinity, okay? This exponential goes to 0, and I'm just left with this expression here, E over LB, and the EMF is 12 volts divided by L, which is 0.36 meters times 2.4 Teslas. So this value in here, so I better put the stuff in here. This is meter. So I have 12 volts divided by, open parentheses, 0.36, and then 2.4. So it's going to be 13.8888 or 13.9, or actually 14, roughly 14 meter per second. So that's how fast it's going to be moving at the end of the day when you wait too long. So let's plot this function in here because it's worth plotting it. I have tau to be 6. So I'm going to use the value of 6 for tau. I have the terminal velocity, which is 14 meter per second. So this expression now in general, V sub t is going to be 14 meter per second times 1 minus exponential of minus t over 6 seconds, basically. And that is the function I'm going to be plotting, actually. So let me stop sharing the screen and share with you my calculator. This is the one I was doing the calculations with, by the way. So what I need to do in here is, are you guys looking at the calculator in here that says Microsoft Mathematics? Everybody? Okay, very good. So I'm going to go to the graphing mode of this calculator, graphing, and I'm going to plot in the function. I only have one function to plot. So I'm going to call it y because it likes to call y for the independent variable. I mean, for the dependent variable is equal to 14, open parentheses, 1 minus e to the power, open parentheses, negative x, because it likes to call the independent variable as x, divided by 6. Close this parentheses and close the second parentheses. And this is the function I'm supposed to plot. So I'm going to say enter. Okay. And graph. Okay. They gave me this. First of all, I know that t is positive, so I'm not going to worry about that. I'm going to zoom out. As you can clearly see in here, it's trying to basically go to a terminal velocity. In a sense, it's not increasing. It increases exponentially initially. So let me change the variables in here. Where is the graph range in here? Plotting range. So I'm going to plot it from x equals to 0 to 100, if I find 100 seconds. 100 seconds is practically infinity. I know the y has to be also 0. And how much was the terminal? It was 14 centimeters. So we're going to stop it at 15 14 meters per second. So we're going to plot it in here from 0 to 15 meters per second in the y-axis. So this is how the function looks like. Okay. Is everybody convinced now that this is 32 seconds? That's way too long. This is, okay, let's me count. 1, 2, 3, 4. So this is a fourth. So this is 8 seconds. 8 seconds is slightly over a tau. So it's in here. Okay, what is that trace? So this is after 8 seconds. 8 seconds, the speed is already 10.285 meters. They told me to find it at 2 seconds. 2 seconds, remember, we calculated it to be, so this is more than 2 seconds. This is actually less than 2 seconds. This is about 2 seconds. How much did we find in there after 2 seconds? Oh, we found the acceleration, not the speed. Sorry about that. Okay, so the acceleration, the speed is 4 meters per second. This is the speed, actually. This is the velocity of the bar after 2 seconds. Again, after 8 seconds, which is slightly more. So after E, which is about 6, the velocity is at 8 meters per second. Okay, so this is about E, about 1 tau. Then after 2 taus, which should be about 12 seconds. So this is the speed now. It's almost the terminal velocity after 2 taus. After 3 taus, which should be about 18 seconds, 18 seconds is right in here. 18 seconds is almost this number. So we are at 13.3 meters per second after 4 taus, which is about 24 seconds. After 24 seconds, we're approaching the terminal velocity now. We're going to slow down. That's the typical behavior of the exponential. But the speed is almost 14 meters per second. Remember, the actual value is not exactly 14, slightly less. But we use in the calculation here, we use 14. So we should really terminate at 14 now. So again, this is after 4 tau. After 5 tau, which is about 30 seconds, we are approaching it. After 6 tau, it's about 36 seconds. We're approaching. This is actually 13.967, 13.97 basically, meter per second. So we're approaching the terminal velocity. If I wait, how long did we wait in here? To the calculator now is giving me 14. After 61, about 10 taus, we are practically at 14 meters per second. Does everybody understand now what's going on with this problem? Yes, no, maybe? Okay, this one person reacted to it. How about everybody else? Okay, very good. Listen, I know I went a little bit detailed about it, and I even shared with you the calculator in here and how to graph this thing. This is a nice tool to have if you have access to it. It helps you basically conceptualize these things and understand them and basically work with these problems and so on and so forth. Those who did not come on Monday, you really have to see the previous problem, problem 59 that we did on Monday. In order to get these two problems, in order to get the benefit from these two problems, in order to understand what's going on in these two problems. The problem from Monday did not have an extra battery. It just was the same rod, we pushed it. So because of this EMF, it's going to basically slow down and it comes to a standstill, okay? And we calculated how far it went. This one is not going to slow down. This is going to continue actually because there is a battery pumping current into the circuit, and that battery will keep it moving, albeit now there is a resistance to that motion, and that buildup of the resistance motion will reach that terminal velocity. So from that point on, it's going to move with uniform acceleration. I mean, with a uniform velocity. So from this point on, from basically, yeah, I know you're saying T infinity. What is T infinity? Well, 60 seconds, if you like, for this problem. Wait 60 seconds, and after that, the velocity is practically 14 meters per second, and it's never going to change. Okay? So that is basically what, in a nutshell, this problem is. So I'm hoping that you guys have learned something from it, because this is something that, okay, problem 65 is identical to this problem, actually identical to problem 59, more so than this problem. Okay? Because there is no extra battery if you look at that problem, just similar to problem 59. Now, problem 62, which is a little bit harder than the other two, the force that you have in there is a restoring force, actually. There is a spring there that is going to help, and you have resistance. This is similar to a problem that I think you must have done in physics 4A, at least if I taught physics 4A, I would have done it. And that is where you have the damped harmonic oscillator. Basically, you have friction, you have viscosity in that case. This is similar to it. I mean, the math would, I mean, the symbols will be different, but the math is identical to that problem. So that is something that you've done in physics 4A. Let me talk briefly about problems 48 and 51 before we jump into the next chapter. Don't forget, we have a meeting this afternoon at 2 o'clock for the lab, okay? So, problems 48. Problem 48. Let's do that first. So, problem 48 says,
We can't
you
see
have a
the
loop in
readings.
here. I'm sorry, I'm not sharing my screen. Thank you. Okay, problem 48. It says basically, again, I'm assuming that everybody has a piece of paper and is going with, if I went too fast on that problem, please go back to it and go slowly and make sure every single step makes sense to you. And if it doesn't, go through it again. If it doesn't, please let me know, okay? Make sure that everything is, no ifs or buts about it. No, maybe I was not focused. That's not good enough. You really have to have full understanding of every single step, and you have to be convinced you yourself before anybody else that it makes sense to you, okay? Do not rely on anything else. That's, you have to really be on top of these things. So, problem 48. Suppose the loop in the figure. So I'm going to draw the loop in here in the figure. Since I have it can I draw it with this tool? And I can draw it a bigger, thicker loop in here. Let's draw it with this size in here. I cannot draw it in another shape, man. Control Z, what am I doing? I'm just drawing one of them. I don't mean to draw too many. Okay, so let's see how we're going to draw this one. Okay. So we have an x-axis in here, or y-axis, I'm sorry. We have the x-axis is in this direction, and that is actually the direction of the magnetic field. So this is where B is. And this is the x-axis. And then we have the y-axis pointing upward. I mean, the z-axis pointing upward. So this is spinning it counterclockwise. Why counterclockwise? I don't like counterclockwise stuff. Well, that's how they drew it. We'll have to live with that. So this is the z-axis. Okay. Whenever you're doing problems, whenever you have things, try to draw them in the standard direction and the standard. So if you have something to draw, work on, and it needs to be somewhere, put it in the first quadrant, where everything is positive, where everything is nicely behaved, so that you don't have to deal with unnecessary signs that are not correct. Like this thing in here, they showed you the omega, and omega is actually in the negative. Okay, that's something that we have to deal with. So is rotated about the y-axis, A, that was A, rotated about the y-axis, B, rotated about the x-axis, C, rotated about on the edge to the z-axis. So rotated here, actually, when it comes to the z-axis, to the edge, okay? Think of it this way, for example. And so the way that they rotated it, they didn't rotate it in the center of axis of symmetry. They rotated it at the edge, okay? And with respect to the z-axis, what is the maximum induced EMF in each case? Well, so they gave us the area A. This area here, A, is 600 centimeters squared. This is when some of you went wrong on this problem from the exam, from the exam. Please pay attention to these things, okay? When they said area A is 600 centimeters, that is not the same as 6 meters squared, because a centimeter is 10 to the negative 2, but then you have to square that. So this is actually one of those two cancels this 2, but it's 6 times 10 to the negative 2 meters squared. Okay, so if I'm going to use SI, I have to be careful in here. And then omega is 35 radians per second. So they gave us the angular velocity, 35. Since they're asking for the maximum, we don't care which direction they put. Okay, because this will change. At some points maximum, some points minimum. So we're just taking the absolute value of one of them. 34 radians per second. And B, magnetic field that is shown in the picture in here is 0.32 Tesla. As a matter of fact, there are 3 significants in this problem, okay? So you have to remember that. So they want basically the maximum EMF, okay. The EMF, if the area is this way, doesn't matter which area you're talking about, doesn't matter which axis you're moving about. So the area is going to be perpendicular. So this is the area A, okay? And if the magnetic field is in this direction B, the angle between them is phi, then the flux is going to be the dot product of B times A. Because B is not changing in magnitude and direction, and A is changing in magnitude and changing in direction only, the angle between them is the only one that is going to matter. So in this case, it's going to be BA times cosine of phi. However, this phi is changing at a constant rate. In this case, when it's around the y-axis. So if I take this derivative, so I will have an omega times t. So if I take the derivative of phi with respect to t in absolute value, again, I'm looking for the maximum EMF. Emax is going to be the maximum of this value, which is just B times A times omega times the sine of omega of phi, or omega t. Okay, there is a minus in there that you're worried about it. The absolute value will take care of that. And since we're looking for the max, this number is going to be 1. Because the sine at most is equal to 1. So the value is going to be BA omega. We have A, we have B, we have everything, so we should be able to find this one. So let me change to a calculator in here in this calculator. So B is equal to, again, 6 times 10 to the power, A is 6 times 10 to the negative 2. That is in meters squared now. Times the flux is 0.32. The flux times the electric field, the magnetic field, times the omega, which is 35. You just multiply every single number in there. So it's 0.62, 0.67. So the EMF max is going to be equal to 0.672 volts. Okay, so that's part A. This is when it was rotating around the y-axis. When it's spinning around the x-axis, though, every time this one's, first of all, the things that don't change, let's say, for example, this area, there are no more or less field lines as this spins. But regardless of its shape, if this one spins out of shape, the other one will pick up some of the values by symmetry. So actually, the area does not change. So when it's spinning around the x-axis, as a matter of fact, the angle between them stays the same all the time. The angle is going to be 0 degrees. So cosine of 0 degrees is 1. So the flux when it's spinning around the x-axis, the flux is going to just be BA. It's not going to change. And A is fixed, B is fixed in magnitude. So in this case, the derivative of the flux with respect to time is going to be 0. That's it. That's the end of it. In this situation, the EMF is going to be 0. So regardless if you spin it around the x-axis in the same direction as the magnetic field, because the magnetic field is taken to be around the x-axis, then in this case, there will be no EMF in this loop. Okay. Now, when you spin it around the z-axis, again, it doesn't matter. When you spin it around the z-axis, at some point, it's parallel to it, and at some point, it's going to be perpendicular to it. So now, you're going to have another cosine of phi, and that phi is going to be the same projection in here as before. So around the z-axis, which is part C, this is part B, this is part C. It doesn't matter where you spin it because the whole area will just change the angle, that's it. So the flux is going to still be given by BA times cosine of phi now, where phi is going to be omega t, and the same value of the EMF max is going to be as before, which is just BA times the omega. So it's BA omega. The good thing about this problem is they didn't ask us to find any direction whatsoever. If they did, then we will have to worry about that. So 0.672 volts. So both cases, that is the same volt, except that when you spin it around the x-axis, there is no voltage because the area and the magnetic flux keep the same direction and with respect to one another. And then, hey, in this case, cosine of 0 is 1. Nothing changes in terms of a flux. So in that case, d phi over dt is equal to 0. And at the end of the day, you have no EMF. So that's this problem. Oh man, I don't even know if we can get into the stuff that I was planning to get into. So let's do quickly problem 51. This will be the last problem that we're going to tackle from this chapter. Problem 51, it says, a flexible circular loop, 6.5 centimeters in diameter, lies in a magnetic field of 1.35 Tesla, directed into the picture, into the plane of the page as shown. So basically, this is what they show you. So they have a loop in here. And so this is where the joint is. This is probably where the spinning or whatever is happening in here. And you have a resistance in here, R. That's it. And they have this point labeled A, this point labeled B. This is a resistance R. And the diameter of this area in here is equal to 6.5 centimeters. And the magnetic field that is pointing into the screen What matters is just this magnetic field, okay? Because no other area is changing except this area. So it's 1.35 Tesla. So that's all we have now for this problem. This is what they say. The loop is pulled at the points indicated by the arrows, forming a loop of area of zero area in 2.5 seconds. Okay, so what they do to it, they come in here, somebody comes in here and stretches it. So they pull on it on this side, physically pull on it, and they pull it on this side. In 2.5 seconds, no, in 0.25 seconds, it shrinks from this, whatever area is right now, down to an area that is equal to 0. Okay? Find the average induced EMF in the circuit. Okay, because this area is shrinking in size, we need to find the flux now. The flux is clearly because the area and the area is actually into the screen. The flux is into the screen. Everything is a magnetic field in the screen. So the flux is simply just the product of the area times the magnetic field. That is it. Okay. Because cosine of 0 is 1, because both of them are in the same direction. However, the area is not fixed. The area is changing as a function of time. As a matter of fact, it was some finite value at t equal to 0, which is equal to the area initially. So this is A naught, was pi times the diameter over 2 squared. And now at t, after t.25 seconds, the area now is equal to A1, 0. So it has shrunk in size. So if I try to find how this function is changing with time, I can do basically the rate at which the area is changing is just delta A over delta T. So the area delta A over delta T is going to be equal. The final value is 0. The initial value is pi d over 2 squared. And the time it took it to do that is t, which is 0.25 seconds. So I can plug in the area, this one in here. I'm going to find the area to being negative pi. I have to be careful in here with this area because I need to write it in SI. Negative pi times the diameter, which is 6.5 centimeters, 6.5, 10 to the negative 2 centimeters. That is centimeters divided by 4, because I forgot to divide that by 2 before I square it. So the area is changing with a rate negative 0.000313331. So the flux then, or the derivative of the flux, the magnetic, the EMF, which is going to be minus d phi A, d phi B over dt. So it's going to be a negative times a negative, it's going to be a positive. This number times the magnetic field, because I didn't multiply it by the magnetic field. So that's the rate at which the area is changing, and the magnetic field itself is 1.35. So I have to multiply this number by 1.35 to find how many volts that is. And the answer is 4.47. How many sig figs in this problem again? 3 sig figs? Yeah, 3 sig figs. So it's 4.48. So it's positive 4.48 millivolt, okay? Because this one it has 0.00 first before that number, okay? Now, I have to find the direction. Since this is shrinking in size, of course, if I want to find, first of all, did they give us R? They didn't give us R. So we can find the current, but we should be able to find the direction. What is the direction of the current? So they all ask about the direction. They don't ask about the value of the current. So they gave us R, we'll find the value of the current, which is just the EMF divided by R. But the direction, okay. This area is shrinking in size. That means less and less field lines are going in. So it's going to compensate for pushing more and more field lines in. So as it shrinks in size, we're going to miss some of this x's, as this one is shrinking down to 0 basically. So it needs to compensate for by pushing some inward into the picture. So that is the induced EMF now. The induced EMF will have a current going into the picture, so its current needs to be clockwise. This way. So the current better be clockwise. Does this make sense to you guys? This is critical. This is the reason why the problem is set up. It's about the direction, no more. Those numbers in there just basically, it's like they throw what you call it, that dust in the eye. That's all. The whole problem in here has to do with the direction. You need to find the proper direction. So again, you understand this one, chapter 21, 9 is for you, is great. This is what's going on. The area is becoming smaller and smaller. As it's becoming smaller and smaller, you're encompassing less and less field lines going in to the screen, because the whole field, magnetic field is going into the screen. So yes, the flux is changing, but it's becoming less and less going into the screen as the area is shrinking inside, as you're pulling on it, okay? Because the field lines are going less and less in, the induced EMF must compensate for that because of Lenz's law, because of that negative sign in the law. So it's going to push a current in such a way that it's going to go into, that the magnetic field is going to go into the screen. So now I know the magnetic field needs to go into the screen. Since that requires a current that is going to curl around it, then I know that the current must be going clockwise. In the previous problems that we did, problem 59, problem 54, I know problem 48 did not deal with the sign. Both of those two problems, the EMF that was generated was going actually, because the area was increasing there. So you're encompassing more and more field lines. So there are more field lines coming into the screen. So in this case, I mean, going into the screen, so the EMF needs to have its own magnetic field coming out of the screen. So that's why in that both of the problems, the EMF that was induced generated the current that was going counterclockwise. This is the opposite now. This is now the area is becoming less and less, so it's encountering less and less field lines. So in this case, it needs to push more and more field lines to compensate for whatever is missing. Does this make sense to you guys? If it doesn't, and I know it's hard, believe me, okay? It's hard even on some seasoned, basically, teachers of physics that I have seen. They struggle with this one, trying to even find it themselves before they explain it. This is something you need to go back to the fundamentals and try to understand it. If you don't, please reach out to me. How's that for a deal? Okay, very good. So you really have to, I know, I mean, it's hard stuff. And the whole Faraday's Lenz's law, actually, the problem with it is not the calculations, honestly. It's really that sign business, trying to find the proper direction of the current. Okay, everything else is actually easy. To some extent, I know probably for you, this is the first time you get exposed to it, so it might sound kind of mountain to climb. But the more practice you do it, because all you're doing is just the derivative and trying to find how that derivative changes, that's all, in terms of magnitude. And that's stuff you must have had. That I know. The other difficulty with physics in general is trying to set up the problem so that you reach that derivative. And that is a common theme that I have seen, at least with some of the engineering students. Just give me the math, I can do the math. But that's the whole problem of physics, trying to get to the math, okay? Trying to reach that level. Once you do that, then anybody can do it. Actually, it's out of your hand at that point. You can just hand it to a math person and tell them, hey, can you get me the derivative, or can you get me the integral, or can you get me the plot this function for me, or get something for it. So, okay. So I hope this is insightful. Again, let me repeat the two problems so that we understand exactly, because I'm hoping that you guys have full understanding of what's going on in terms of the sign business. In the problem 59 and 54, both of them, what you had a rod that was moving this way, We have rails in here, and the field lines were going into the screen. So as the rod is moving in this direction, in either case, you are getting more and more field lines that were not in this area to begin with. You're including them now as this rod moves in onto them. So at some point in the future, it's going to be here. Okay, so this were not there to begin with, at least this two. This is outside anyway, so it doesn't count. What matters is the ones that the overlap area, that's all. Okay, now you have the EMF that is going to be generated in such a way to make up for or to compensate for this ever-increasing field lines into the picture. So it's going to make up two of its own to compensate for this two. So it's going to make one coming out and another one coming out. How is it going to create a magnetic field? According to Ampere's law, it has to have a current. And that current, because the magnetic field is coming out of the screen, has to go counterclockwise. So the current that is generated because of this motion has to go this way in order for it to create magnetic field pointing out of the screen. So this is where the I is. In this situation, in this problem, what is it? 51. The picture is reversed though. What's going on in here? You have a loop that is shrinking in size. Okay, so the magnetic field is into the picture. So this is how many field lines there are right now. Immediately after this one, in the future, after this one will become like this. Stretched like this. Okay. So there are less field lines that were included before. Here they were. Now they're not. They're gone. Okay. Because it's shrinking in size. So at some point we're losing them. And now you're worried, oh, didn't we pick up one probably or half of one in here? Maybe and another half in here. But overall you're going to get less. Do you understand? Because the area is becoming less and less and less. Okay. So there were actually, you missed one in here, if that's you're being picky about that, and another one in here. So it's trying to be, okay? So at the end of the day, you will have less and less field lines going into the screen. So this guy must compensate for them by pushing for more into the screen. In here, it compensated because you included more that you didn't have before. Now, it compensates because it lost some, so it needs to push some into the screen, the ones that it lost. So I got 2 in here, I got 3 plus 2, that's 5, minus 2. So it needs to push at least 3, okay? If you're picky about this business that you picked up some and you lost some, but there is a net loss. So it needs to compensate for the net loss. So now the magnetic field is going into the screen. So this is the magnetic field that it has induced. It's going into the screen, and the current must going, in this case, clockwise. So the current that is generated in here, because they ask about the direction for it, it has to be clockwise. Does this make sense to you guys now? Okay, very good. Very good. How's everybody else feeling about it? Okay, very good. Thank you. So again, this is, I know a lot of these things are new to you, and the only way to remedy this new things is by making them old, okay? The only thing to basically fix that is by making it old, and the only way making it old is actually by doing problems. When you do problems, it becomes a little bit of ancient story that you say, hey, I know this thing's how it works. So that is the only way to fix this thing. So let me jump into, let me share the screen again. At least introduce the next idea. I was hoping to get into more detail on it, but that's fine. We have had some fun, at least with chapter 29. So chapter 30. Before I do chapter 30, there was something that was actually needed from way back in chapter 28. So let me introduce that, which is very important, and that is the solenoid. Oh, I don't mean to write it in red. So what a solenoid is, think of your, for example, when you run out of paper bathroom paper, paper tissue for the bathroom or even for the kitchen, you will end up with this cardboard basically. Can I draw it better with those tools that I know I have? Okay, let me draw a line in here. And let me draw another line in here. Or Control C it, Control V it. Okay, pick it up. Okay, so they look more or less normal. Let's bring a... Okay, this is how it looks like. Control Z. Control C, Control V. This is how it looks like more or less, okay? So what you do in this case, you come in and you wrap a wire around it, okay? Tightly wrap it. So you come in here. So I'm gonna bring a wire in here and I'm gonna go around it and come back from the other side and wrap it around it and come back from the other side and wrap it around it and so on and so forth. You guys got the picture, okay? So if you ever had a problem with your alternator and you have an old car that you don't have access to its parts, so you can go to those mechanical shops and they can build basically or rebuild the alternator for you. This is what they do, more or less, albeit they do it a little bit differently. They have machines that do that for them. It's not a person sitting there. That's going to be too much. Anyway, so this is basically what the solenoid look like, okay? Now you can dispose of that thing if you like, or you can keep it, or you can put an iron there, piece of iron in it to improve the situation and so on and so forth. So what you have in here is you have a current. Let me draw the direction of the current so that it's going to go clockwise again. So again, there is a current flowing in here, so it goes around and it comes back, it's going to come out in here. So in every one of this is going to go this way. At the end of the day, it's going to emerge in here, in this direction. So that is basically how this looks like. So this is a solenoid. My question is, if I have a current I running through this one, is what is the magnetic field inside this region of space? Because this is going to behave like a magnet. This is actually what an electromagnet is. So what I'm going to do in here, I'm going to apply Ampere's law. So what I'm going to do before I do that, I'm going to make a mathematical cut, not a real cut, because if I cut this one with scissors, I have no current flowing. I will cut the current. I will start the current immediately when I make the cut, and that is useless. So what I'm going to do instead, I'm going to have a mathematical cut in the shape. So this is how it looks like. Can I pick up one of these lines? This one. And this one maybe? Control C, Control V. So this is how the wire looks like. And this is how, or Control V it still. This is where the second wire is. So assuming I made a cut in it, this is how it looks like. This is a mathematical cut, not a real cut. Don't do it, because if you do it, you're not going to have any current flowing through the... So this is how it looks like. Okay. Again, at this point, the current is going into the screen. As far as I'm concerned, in here, it's going onto the screen. In here, it's going into the screen. So this is the current, not the magnetic field, okay? And this is not a real cut, as I was saying. And in here, the current is coming out of the screen. As you can clearly see, it's coming out from this side. And in here, it's coming out. And in here, it's coming out. Everywhere I look at it from this side, it's coming out. This is, again, I cannot emphasize enough that this is a mathematical cut, because if you cut it really, there would be no current. End of the story, okay? So this is a mathematical cut. Okay? So there is a wire that is going in. So from my vantage point, that is what's going on. So my question is, assuming that this is an infinite solenoid, so this is, I'm going to make it very long so that I don't have to worry about what's going on in the edges in here. Okay, so this is an infinite solenoid. In other words, it's too long compared to its radius, that's all, okay? So this is what I'm saying in here. What is the magnetic field in here? What is the magnetic field in here? And if I know it here, I probably will know it here too. So for that, what I'm going to do, I'm going to apply Ampere's law. I know we still have about 10 minutes, so we need to do that quickly. So the Ampere's law, I'm going to take a mathematical loop. Again, this is an Amperian loop. Amperian loop is not a real loop in space, okay? And ask if there is a magnetic field in there, what is its circulation? Well, through this shape in here of length or width, length L and width W, then if there is a magnetic field in here, it's going to be, if there is a B on this side, first of all, in terms of the magnetic field, in terms of the direction of the magnetic field. By symmetry in here, this magnetic field must be, because it's an infinite rod. It's an infinite, solenoid. Then in this case, if I move it up and down by symmetry, the magnetic field must be pointing in this direction only, okay? And it must be the same at a given distance. So this magnetic field at this entire distance must be the same. And it's also the same for this entire distance. So this is B1, and this is probably B2, okay? And in here, it's perpendicular to the displacement in the loop by symmetry again, okay? Because the only way for me to argue for because this is an infinite loop, and if you tell me that has any other direction, then I'm going to basically move it up and down, and then the value should change if it is really a direction other than this two. So again, the magnetic field is going to be 0. The dot product is going to be 0 in here. So there is no contribution in the L direction. There is no contribution in the L direction. The only contribution that is going to happen is this between B1 and B2. Here, the magnetic field, if I'm circulating in this direction, this value is going to be negative because I have B1 times the displacement, and displacement in the negative direction. So this is going to be minus B1 times W, and this is going to be B2 times W, okay? And in here, it's 0. You ask, hey, I don't know what B1 is and what B2 is. This is what I'm going to do. I'm going to make L goes to infinity so big. If L goes to infinity, I expect no magnetic field far away from the wire, because at infinity, far removed from it, there will be no effect whatsoever of this wire on anything. So B2, when L goes to infinity, must be equal to 0. Since the difference between them must be equal to the current enclosed, and there is no current enclosed. So what I end up with is minus B1 times W plus this magnetic field, which is 0 when L goes to infinity, which is 0, must be equal to mu naught times the current enclosed, and there is no current enclosed. So this is 0. That means B1 is equal to 0. So for an infinite solenoid, there will be no magnetic field outside of it. End of the story. Because I can push this distance all the way to the edge of this solenoid, and I still find 0. So B on this side is 0, and so is B on this side is 0 by symmetry. Actually, if I do the same Ampere loop on the other side, it's going to give me a magnetic field that is 0. However, when I cross over between the two regions, I will have a finite magnetic field at this point. Okay, so let's see what's going on in this region. So if I cross over in here, again, by symmetry in here, the magnetic field is 0 here. I just made the case for it. The magnetic field in this direction in here, let's say, for example, it's some value, which I'm going to assume it's going to point in this direction. Okay, and let's see if that's going to be true or not. We're going to see that. Okay. Again, I'm going to go counterclockwise during my circulation. So in this case, it's going to be negative B times this width W. The W is a hypothetical value. It's not a real one, okay? The W is not a real, it's because part of the Amperian loop, and the Amperian loop is all of it is a made up shape. It's not a real shape. So W and L, both of them are made up. That's why I pushed L to infinity in here to make my case for B equal to 0 everywhere, not just in infinity, outside of the solenoid. On this side, again, it's perpendicular, so it's going to contribute nothing. On this side, B, I just argued to be 0. So that's the only value that is equal to. It's going to be mu naught times the current enclosed. Now I need to know, how did you pack those wires? You tell me I made N turns per meter. This is how closely they were tied. Remember, I had this one in here. This is how closely you wrap them together to one another. Okay, so that is the number of turns per meter. So if there are 10 of them, you have 10 wraps per meter, 10 turns per meter. If you have 123 of them per meter, then you have 123 of them per meter. But you didn't take a meter, you took a W of them. So this distance from here to here is just a W. So it's going to be N times W. This is how many they are, times I naught, times I. And I is the same current, with the exception that this I is going into the screen. So this is a negative I. Okay. Obviously, the W need to cancel from both sides because it's a made-up number. It's not a real thing. It's a made-up part of the imperial loop. And the negative cancel the negative. And we have this nice result in here that is worth remembering, mu naught Ni. This is the strength of the magnetic field inside the solenoid, where I is the current that is running through it. N is the number of turns per unit length. So N is the packing of turns per unit length. It's just a number. Okay, so many of them per meter, if you wish. Okay, so this is one of them. I know we have about 3 minutes, and then we're going to finish this one quickly. So we found the magnetic field, and here it applies for the other one too. Okay. The other one, if I did it this way, it's going to the circulation is going to be still counterclockwise. The magnetic field in the same direction, and the current is positive. Everything is positive, so it's the same value everywhere inside the magnet and inside the solenoid. So this is the magnetic field and how you find it inside the solenoid, infinite solenoid. Let me do another solenoid in here quickly that is used in industry a lot. So let's assume that this is this shape, and let's take another one similar to it, except it is Control Z. And put them one inside the other, like this, okay? So this is what is known as a solenoid. I mean, as a toroid, okay? Toroidal, I don't know how to, honestly. Solenoid. This is also used in the industry extensively. So what I do in this case, I'm going to bring the wire, I'm gonna wrap it this way, okay? I wrap it around. When it comes out, wrap it around. When it comes out, wrap it around, and continue doing this. Okay, so this is how it is wrapped now. I have N turns, period. I don't have them per unit length. I just have N turns all together, okay? Same thing, I'm going to have a Amperian loop anywhere outside. So again, I'm going to make a mathematical cut in this. So this is how it looks like. Control C, Control V. So similar to the previous problem. So we're going to make not a real cut. Again, if you really cut it, you're not going to end up with nothing. So you better not do that cut again, okay? So if I look at the current, again, I have to choose the direction of the current. It doesn't matter which, honestly. So if the current is going in this direction, so it's going to go this way, this way, this way, all of them. Why did I draw so many? It's really not good. And it's going to come out to here, okay? So again, what I'm going to do in here, I'm going to make a mathematical cut, just like I did in the previous one, where the current is going to be coming out of the inside and going into the outside. So again, similar to before, what color did I draw for the currents? Was it red? Yeah, let's do it the red thing. So the current is going in here. And it's going coming out in here, and they have to be exactly, they have to match, okay, because each wire is actually the same wire, and this is not a real cut again, this is just a mathematical cut, okay? I'm assuming the numbers are the same. If not, put the exact number that are they match. Otherwise, you have a problem. So now, again, if I do outside, if I'm interested outside, I'm going to make up this shape in here, which is actually a big circle, okay? And I'm going to argue by symmetry the magnetic field must be circular in this case. So this is a circle of radius r, by the way. So the circulation of the magnetic field is going to be counterclockwise. So it's b times 2 pi r. This must be equal to the current enclosed. And the current enclosed is mu naught times some are negative, some are positive, and it's exactly the same number. So it's going to be times 0. So B outside is going to be 0. B inside also is going to be 0 for the same reason that does not enclose any current whatsoever. So it's going to be B times 2 pi mu r is equal to 0. The only reason why this is 0, because it's the exact number that are going in is the same number that is coming out. But in this surface now, for r bigger than the inner radius but less than the outer radius, I have a finite value in here. So what I have in this case, again, the circulation is in the positive direction. So what I will have in this case is B times 2 pi r that is the radius of the circumference. I mean the circumference, the perimeter of the circumference times of the circle. So the circumference of the circle, I should say, is equal to the current enclosed, and the current, there are n of them, each and every one of them carrying I. So in this case, the magnetic field will be simply mu naught Ni divided by 2 pi r. Okay, so these are the two types of solenoids that you will find in the industry. When we meet again on Monday, we're going to finish the discussion and build ourselves the inductors and finish the chapter 30. Okay, I'm going to stop in here. I'm sorry we went 2 minutes over. So I'm going to meet you guys around 2 o'clock for the lab, and that's the day today. Thank you. Let me stop sharing the screen first and stop recording.